Now as an application, we give an example. So suppose that ft is given by 1 over root t. So of course we can easily see that for alpha greater than half and less than 1, t to the power alpha f of t is given by t to the power alpha minus half, which goes to 0 as t goes to 0 plus if alpha is greater than half, because now this is a continuous function. Therefore, this is ft is a function which has a vertical asymptote at 0. So ft has a vertical asymptote at t equal to 0. Ft is piecewise continuous on any interval small r to capital R, where 0 less than r less than capital R less than plus infinity. It is a piecewise continuous function. In fact, it is a continuous function for this interval small r to capital R. And thirdly, that ft is of exponential order. In fact, as t goes to infinity, this ft goes to 0, and therefore it is always bounded above by the exponential function. So for example, if you take the interval t from 1 to plus infinity, so in this interval 1 to plus infinity, the graph will look like something like this. And of course the exponential function, so this is 1 over root t, and the exponential function will be something like this. So of course ft mod of ft is less than or equal to e to the power alpha t for t greater than or equal to 1. In fact, you can take alpha to be 1 also. So it's less than exponential function for all t greater than or equal to 1. So therefore this is of exponential order, and this function then satisfies all the conditions, sufficient conditions for the existence of Laplace transforms. Therefore the Laplace transform of ft exists, and we can compute it explicitly. 0 to infinity 1 over root t exponential minus st dt. So for this we make a change of variables. We put u equals st, which means that du is ds dt. Here s is assumed to be positive, and so we have our integral is again from 0 to infinity, because s is positive, it's from 0 to infinity exponential minus u, and then you have 1 over u by s to the power half, and you have here s du over s. So this is equal to 1 over root s. So here half factor and here half factor cancel out, so you get root s, 0 to infinity exponential minus u to the power minus half du. Now this integral has a term as a special function, and this is known as a gamma function, So for alpha greater than minus 1, gamma of alpha is the integral 0 to infinity exponential minus u t to the power alpha t to the power alpha minus 1, sorry, u to the power alpha minus 1 du. So this is our gamma function, which is defined for alpha greater than minus 1, and those of you who have seen this gamma function before will know that the gamma function of n plus 1 is n factorial when n is a positive integer. So this function turns up in many places, and it's a useful function, and it falls in a class of special functions that are used. So here we have our gamma half. So therefore our integral 0 to infinity 1 over root t exponential minus st dt is equal to gamma half over root s. Similarly, we can do this for any alpha greater than minus 1. We will get that the Laplace transform of t to the power alpha is equal to gamma alpha plus 1 over s to the power alpha plus 1, and defined in the region s greater than 0. So this computation is the more or less the same as in the case alpha, when alpha is minus half. Here alpha is assumed to be greater than minus 1, and in our previous example alpha was minus half. So for in general, if alpha is greater than minus 1, then the formula is simply given by gamma alpha plus 1 divided by s to the power alpha plus 1, and it is derived exactly as in the same way when alpha is minus half.